Welcome to the third video of this series in which we're trying to write a DPD simulation for a polymer in solution, or let's say dilute polymer solution in C from scratch. And we've made quite a bit of progress in the last two videos, setting up the initial simulation, implementing the harmonic force between monomers in a polymer chain, and also the start of the cell list. In this video, we are going to really wrap up the main parts of the simulation by finishing our implementation of the cell list to calculate pairwise forces and implementing the velocity-Verlet algorithm to integrate the equations of motion to get the new positions and the new velocities of all of our particles in response to the forces that they experience. And so just a couple things. I wanted to make some changes to the code up front just to kind of make our lives a little bit easier when we start to run our simulation. And the first is that for the calculate forces function, I want to pass an integer parameter called prod, which is short for production, to signify whether we are equilibrating our system, where all of the particles will interact with the same strength in the conservative force, or whether we are in the production phase where we could have different strengths of interactions. And so in general, when we run these simulations, we'll equilibrate our system for a while so that the radius of gyration stabilizes, so that the temperature stabilizes and things like that. And once that occurs, then we will start the production stage of the simulation where we start to collect our results that we can analyze later. So I want to pass that parameter in, which means that starting here, when we first make the list of interacting particles and calculate forces, I'm going to pass a 0 here to signify that we are not in the production stage, but we are in the equilibration stage. The other thing is I want to clean this up a little bit. I mean, certainly we want to calculate the radius of gyration and print things to the screen at regular intervals, but we don't want to do it this way and we don't want to do it yet. So we're going to come back later and write things to the screen. So I'm going to delete those lines that we added last time. And the last thing that I'm going to do to set this up for us is I want to define some parameters, and maybe we'll put them up here. I want to define, let's say, output. Maybe we'll call this calculation frequency. How many, or after how many time steps are we going to, let's say, calculate the radius of gyration, calculate the temperature, calculate whatever we're interested in? And I'm going to set this to be every 100 steps right now. And I'm also going to define, let's say, out frequency. And I'm going to make this, let's say, 1,000. And this is how often we are going to write our coordinates to disk. And so let's just make a note of this here. Calculation frequency, how often we calculate our GT, etc. And then out frequency, how often we write our coordinates to disk, so that at the end of the day, we can make, let's say, some nice movies in a Vito or something like that. Okay, so that kind of sets us up here. And so what we're going to do is take a look at our calculate forces function. And of course, here we're going to have to update this to accept that parameter production. And the other thing that we need to do that we didn't do last time, notice we calculated the average bond length. So in order to really calculate that, we need to normalize it, right? And so at the end of the day, once we've gotten all of those separation distances between pairs of adjacent monomers, we want to get the actual average of bond length. I don't want to say normalize, we're not actually normalizing it, but we need to divide by the number of polymer chains and then the number of bonds, not the number of monomers. So we need to multiply this by n-1. And this should be a double precision number. And then that sets us up. Okay, so in order to go in and actually calculate all of the forces, all of the pairwise forces that we've got, we have to define a few more variables. Okay, so now we're going to go through all of the different cells that are in our simulation and see who is in that cell and then calculate the conservative, random, and dissipative forces. So the indices we need, we're going to need a couple more. We're going to need just some more integers to iterate on. Sorry, you know how I feel about my spaces at this point. And we have index I and index J, so that's good. We're going to need some indices that are going to denote which cell that we're looking at. Okay, so we're going to iterate through all the cells in the system and then look at all the neighbors. And so these indices will tell us what cell we're in. And so we're going to have to, of course, calculate the index of cell 0 and cell 1. Remember, cell 0 is going to be the cell that I'm processing. Cell 1 is going to be one of the 13 neighbors of cell 0, or it could be cell 0 itself. And so cell 1 is going to take on 14 different values for every cell that we look at. So we've got the separation distances. That's good. We're going to use those again. We also need some values x trans, y trans, and z trans. And these are going to, for most of the time, these are going to be 0. But sometimes they'll be equal to plus or minus the dimension of the system. And this is to take into account the periodic boundary condition, so that if one particle is on the far boundary of the system, it will interact with the particles that are nearest to it, which would be wrapped back on the other side. And hopefully you'll see how that works as we implement that. Fnet, Fcomp, that's good. Just for clarity, to make the algorithm a little clearer, I'm going to define the conservative force, the random force, and the dissipative force, and this will just make it easy for us, it'll make it easy for us to read the code and understand what's going on. And then we need some other things, right? So if you think back to what's in those forces, we've got the interaction strength of the conservative force. We've got that random number with 0 mean unit variance for the random force. We need the dot product between unit vector in the direction of r and the velocity difference between particles I and j. Weight factor for the random force and the conservative force, and weight factor for the dissipative force. And I believe that is everything. I'm going to put one other parameter here, Pij, and I'll show you what that is when we get to it. This is going to help us to determine very efficiently what the interacting particle types are. So prod is going to play a role in what the value of Pij is. Okay, so with that, I think we have everything we need. So let's go down to where we left off last time. And now we need to process all of the cells and their neighbors and determine the values of these forces. So essentially what we're doing at this point is we're going to loop through those indices NY, NX, and NZ. And did I forget to put those on here? I think I did. Let's go back and look. There's so many indices here. I am missing those. So int NZ, NY, and NX. So these are the indices of neighboring cell, indices of cell 0. Okay, so let's take a look at what that means when we implement this. So we want to loop through all of the cells that are in our system. So let's do the loop this way. So for k equals 0, this is going to be the index in the z direction. K is less than nz, so this will go through all of the cells, all of the blocks of cells in the z direction. Okay, so that's the first loop. The second one, though, we need to loop through y also, right? So we've got j equals 0, j is less than ny, j plus plus. And that will be looping over all the cells in y. And then finally, we need, these spaces. I don't know why I'm so particular about them, but I am. Finally, we need to loop over all of the cells in x. So I is less than nx, I plus plus. Okay, so that gives us that. So when we do that, now for each value of these integers I, j, and k, we can calculate the index of cell 0 based on these, right? So cell 0 would be, how do I want to do this? Let's get it in this order. So it'll be k times ny times nx plus j times nx. So stride in this direction, the stride of in the z direction, which is those big blocks, plus I. So now we've got a unique identifier for our cell on the basis of these indices here. So that's good. And now what we need to do is we need to loop through the 13 neighbors plus cell 0 for, let's say, to find interacting pairs. So that means we need another index for L is equal to 0. L is less than 14, L plus plus. Okay, so maybe it's not clear at the moment what I'm going to do, but let me show you. Remember that there are 14 elements in these NIX, NIY, and NIZ arrays. And so if I iterate through each of these elements of all three of these arrays, these are going to give me the indices of the neighboring cell for cell 0, including cell 0 itself, right? If these are all equal to 0, then cell 1 will be equal to cell 0. And then in all of these, we're going to specify the cell in the different direction. So that's what we're doing here. So let's see. If I go down to calculate force, we are going to start doing that here. So what we need to do is, now that we've done this, we need to get the first member of cell 0. Okay, so the index of that particle is going to be the head particle of cell 0. So that's how our linked list works. And if we wanted to find the next particle in the cell, we would say IDXJ is equal to cell list IDXI. Okay, so this would be the first particle in the cell, the next particle in the cell, the next particle after that would be cell list IDXJ, and so on and so on. So that's how our linked list works. But we don't actually want to do this yet. What we really want to do is we want to compute the index of cell 1. Okay, so that's the cell that we're processing cell 0 with. And it could be equal to cell 0. So the way that we would do that is the index, the neighboring index I, will be equal to I plus NIX of L. The neighboring index of J would be J plus NIY L. The neighboring index of K would be K plus NIZ L. And so now we can calculate cell 0, and I guess I really don't need a comment for that, right? Cell 1 will be equal to, we would do it in the same way. In fact, let's stop a bit. Let's not calculate it yet, because we need to consider the periodic boundary condition first. Okay, so what I mean by that is, let's say that, let's look at the index in X first. So if Ni is greater than nx minus 1, that means that we've left the system in the positive x direction, right? We've gone past the size of the system. And so in that case, we would want to wrap back to the start of the system in the x direction. So Ni would be equal to 0. That would be the first cell in the x direction. And we would also have to translate the coordinates of our particles by minus Lx. Okay, so let's line those up. And if we're going to do that, we should really initialize these. Okay. So we've got that. That's what happens if we're on the plus x edge of the system. But what if we're on the 0, the x equals 0 boundary, and we're looking for neighboring particles? Well, the particles to our left, that neighboring cell doesn't exist. That neighboring cell would be all the way on the other side of the system. So the other option is that else if Ni is less than 0, that means that we've really gone in the wrong direction, right? We need to go to the plus Lx side of the system. So Ni would be equal to Nx minus 1 in that case. And the amount that we need to translate the separation distances between the two particles would be equal to Lx. Okay, and that handles the periodic boundary condition in X. Now we just need to do the same for Y and Z. So we've got, what, 3, 6, 7, 8, 9 lines here. So let's just paste that. And so in this case, we're just going to change everything, right? If Nj is equal to, or is greater than Ny minus 1, then Nj is equal to 0, and Y trans is equal to minus Ly. And if Nj is less than 0, then Nj is equal to Ny minus 1, and Y trans is equal to plus Lx. All right, so we got that. And then one last time in Z. So if nk is greater than nz minus 1, then nk is equal to 0, and z trans is minus lz. And if nk is less than 0, then we want it to be equal to nz minus 1, and z trans would be lz. Okay, so basically the reason that I did that first is this is giving us the index of the neighboring cell, but we need to make sure that we're not on the boundary. And so then we're going to check to see if we're on the boundary and need to correct those indices to account for the periodic boundary condition. And so at this point in the code, we know what the correct indices are, and now we can calculate the index of cell 1. So cell 1 would be ni plus, in fact, let me do it the same way that we calculated cell 0. So this would be nk times ny times nx plus nj times nx plus ni. Right, so completely analogous to how we calculated the index of cell 0. And so now that we know the index of our neighboring cell, we just need to get the first particle in that list, right? The first particle in that cell, and we're going to process, let me back up here, we're going to process this particle, which is the first particle in cell 0, with all of the particles in cell 1. Okay, so this value, index I, is going to stay the same, but down here, we need to get the head of cell j. So the index of j will be the cell head of cell 1. And that works just fine, right? There's nothing wrong with that. However, what if cell 0 is equal to cell 1, right? That's not going to work in this case. We're going to end up processing index I with itself. So if cell 0 is equal to cell 1, then index j should actually be the list, the next particle in the cell of cell 0. I hope that makes sense. And now what we need to do is we need to just loop through all the particles until we reach the end of the cell I and cell j. So while index I is greater than -1, remember, if that is equal to -1, that means we've reached the end of the cell. And we also need to say while index j is greater than -1, do all this stuff. So this is going to be the bulk of our function that calculates the interparticle forces. And so now that we have this, we can calculate the separation distance, right? So dx would be equal to x idxi minus x idxj. And notice, unlike with the harmonic force, we're just using the normal arrays, right? Because we really do need to consider the periodic boundary condition here, because we're interested in the separation distance between a polymer chain and other particles that belong to different molecules, either solvent molecules or other polymer chains. Whereas in the harmonic force, we are only interested in the separation distances of things in the same molecule, and so we didn't have to worry about where it was in space so much. So the same thing here. So difference in the y coordinates, and dz is equal to z idxi minus z idxj. Now we run into a problem here though, because this isn't taking into account the fact that you could have particles on the boundary. So this is why we needed to create those variables x translate, y translate, and z translate. And most of the time, those variables are going to be, the values of these variables are going to be 0. But if your particle is on the boundary of the system, then these will take on either plus or minus the dimension of the system in that direction. Okay, and so once we have that, we can calculate dr, square root of dx squared plus dy squared plus dz squared. And now we need to see, will these particles interact? Well, they're only going to interact if they're within a distance of rc. So if dr is less than 1, that's what we set rz to be, then yes, they will. They will interact. And so here's where that Pij variable came in that I introduced earlier. So we need to determine the strength of the conservative interaction. So let's set this equal to prod. So this will be 0 if we're equilibrating the system and 1 if we're in the production stage, times the particle type of I times the particle type of J. So if we are equilibrating our system, this value will always be 0. If we are not equilibrating our system, then this value will be +1 if the particles are of the same type, right? So -1 times -1 will give me +1, or +1 times +1 will give me +1. But if the particles are different types, so if the polymer chain is interacting with the solvent, then I would have a particle type of 1 multiplied by a particle type of -1, and that would give me a negative number. So this one value here will capture all of the different types of interactions I can have. And so now I just need to choose the interaction strength. So I'm going to use the switch command on Pij. And the reason I'm doing this and not a conditional statement, like an if-then statement, is computationally switch is much faster than if-then statements. The way the compiler optimizes the code into assembly and machine language with the switch command is way more efficient than using if-then statements. So if I'm running this function over and over for millions and millions of times, the savings that I'll get by switching here versus using if-then statements will really add up into and result in a faster code. So I can do this pretty easily, right? So if, for example, Pij is equal to 0, then what happens here, let's just write the comment so we're clear on this, is we are equilibrating our system. So A is equal to AII for all I and J. The same thing is true here. So if we've got a value Pij is equal to 1, then we know that the interaction strength should be that of the same particle type. Okay, so either of these conditions, I should set the strength of the conservative force to be AII that we defined in param.cfg. However, if we get -1, then we know that the strength of the conservative force should be AIJ. And there's no other values possible the way we've written the code. So I could, if I wanted to be safe, put something here and I could say, hey, the particle types don't make sense and exit the simulation, something like that. You're welcome to, but I just don't see the value in it. Remember, we're trying to make our code as fast and efficient as possible. So let's close the switch, and now we've got the strength of the conservative force. And let's put some comments in here again to remind us. So the particles are same type. So we've got polymer-polymer or solvent-solvent. And then down here, if this is equal to -1, then we've got particles are a different type. So we have an AB type interaction. Okay, so now we've got that. What else do we need to calculate? Well, we need to calculate, I've got too many braces here. Let's see what's going on. I feel like I've messed something up with these braces. We're going to have to count these later. I don't know if VI added them automatically or what, but it's not going to compile. We're going to have to track these down to make sure that everything's okay. Okay, so the particles are close enough to interact, and now we need what? Well, we need to determine, in addition to the coefficient of the conservative force, the strength of all the forces are going to depend on those weighting terms. So calculate the weighting terms. And we know that WR, in this case, is equal to 1 minus ER. But remember what we did in the conservative force, or sorry, in the harmonic force. We divided through by dr because we're taking the dot product between the force and all of the different directions to get the components. So ahead of time, I'm just going to go ahead and divide through by dr. So we have 1 divided by dr minus 1. So this is actually WR divided by dr. Right? And what we did is we made the choice, and again, this is not required, but it's a very common choice, that the dissipative weighting term is just going to be the random and conservative weighting terms squared. And what this means is that if I look at this term right here, I've divided through by dr. So this is actually equal to WD divided by dr squared. And we're going to have to make sure that that makes sense. Okay, that that's correct, because we could get into trouble there. What else do we need? We need a random number for, for the random force. So theta ij, remember, it should have zero mean, so it should be centered about 0, and it should have unit variance. I think in the first video I said that this effectively amounts to a random number between -1/2 and +1/2, centered about 0. That's not correct. It's centered about 0. It should be between -1 and +1. So the way that we would do that, since rand3 gives us a number between 0 and 1, the way to do that would be to calculate this as 2 times rand3. That will give us a number between 0 and 2 minus 1, which will give us a number between -1 and +1. And if we do it this way, we're calculating a random number for all different values of theta ij, and we're calculating a different random number at every time step. So this takes care of the condition in terms of whether the random numbers are correlated or not. They should not be correlated. All right, so with that, we need the dot product. And this is actually between a unit vector and Vij. Okay, so what this means, let's just calculate the dot product first. R dot V will be dx times Vx minus Vxj, that's the x component, plus dy times Vy minus Vy of j. Let's fix my typo. Got that, and then plus the z component, right? Times Vz idxi minus Vz idxj. Sorry that that wrapped around like that. But it is what it is. I just want to make sure I declared the dot product. I did? Okay, very good. So we've got the strength of the forces, we have the random number, we have the dot product between r hat ij and v. So what can we do? Let's add to the potential energy. So the potential energy plus or minus, or plus equals, the random and dissipative forces overall should cancel out. And so the only thing that's adding to the potential energy is due to the conservative force. So this will be plus 0.5 times the strength of the conservative force, and then times 1 minus dr squared, right? So it's a harmonic force, but we cut it off at RC, so it's kind of like half a parabola. And I think that's it. So now we can compute the forces and add them to our force arrays. So compute the conservative, random, and dissipative forces. So the conservative force is going to be, what do we say, A times that weighting factor. The random force is going to be sigma times the strength of the random force times theta ij. And the dissipative force is going to be minus gamma 1. Remember, we had to put the gamma there because the gamma is taken by the gamma function. Times the strength of the dissipative force times r dot v. Okay, so here's where we come to the part where we need to think about whether or not this definition of the dissipative weighting force is correct, because we're dividing it by dr squared. So if you think about it, when we do this, one of the drs is going to come up when we take the dot product between fd and, let's say, dx, dy, dz. So one of those is already taken care of. Now what about the second dr in the denominator here? Well, this dot product, r dot v, is actually between a unit vector in the direction of dr and the difference between the velocities of the particles. And so right here you can see that dx, dy, dz if you were to get the magnitude of this vector, this would not be a unit vector. So the second value of dr here that shows up in the dissipative weighting term is dividing through dx, dy, and dz to make this a unit vector. So that means that we're correct. This is totally fine to do it this way. All right, so with that, we can just get f net, and this is fc plus fr plus fd. It's not necessary to do this, but I wanted to do it just to kind of make the code a little clearer so that we could kind of conceptually see what we're doing and compare it with a paper like Root and Warren or something like that. So that's fine. And now we just need to compute the components of the force. So we do this just like we did with the harmonic force, right? So the component in the x direction will be f net times dx. And then we can say f of I dx I plus equals that one. And then Newton's third law tells us that this should be minus that. You can look in the y direction. What am I doing here? This isn't f, this should be fx, right? Okay, now we've got the y component of the force, so the y component goes into those arrays. And we can do it for the z components. So f net times dz, fz plus equals f comp, and minus. And so you can see kind of the way that we've done this. We're always adding a force and subtracting a force, adding a force, subtracting a force, right? Equal and opposite. And so what this means is if we were to calculate the momentum of our system, though the momentum should not change in our system. The momentum should be conserved. So if our initial momentum is 0 for our system, and it should be because of the way that we did everything, right? Subtracting off the net drift and things like that, then we would want to check the momentum of our system occasionally to make sure that it's equal to 0, to make sure that the simulation is running correctly. If the momentum starts to increase, if the magnitude of the momentum starts to increase, then we know that something is wrong. Okay, so I've got all these braces down here, and what I'm going to do next is I'm going to take a little break and I'm going to go through and make sure that they are matched to everything, and I don't want to waste your time doing that, so we'll be right back in a second and we will have the correct number of braces down here. Okay, we're back. So I tracked down all of those braces. There were just a couple of extra ones that I probably typed in. But here's where we are. So here we've ended the check of whether the particles are within a separation distance that would give rise to a non-zero interaction, right? Are they separated by a distance less than RC? So once we've done that, I mean, effectively all we've done so far is we've gone through each cell in the system, and for each cell that we look at, we've gotten the first particle that belongs to that cell, and then we've processed it with that cell and the head of that cell with 14 of its neighbors. And for each of those neighbors, all we've done is gotten the top particle, the first particle that belongs to that. So what this means is that down here, once we've checked to see whether the first couple particles are within an interaction distance or a separation distance that gives rise to an interaction, what we need to do is get the next particle. So that would be the cell list of IDXJ. So this gets the next particle in cell 1. Okay, and this will keep going until the cell is empty. And when the cell is empty, this value will be -1. And so that will exit us out of this while loop. And so when it does that, what we need to do is we need to go back to the top of the cell. So we need to say index J is going to be cell head of cell 1. So we go back to the top, and we're going to process the next particle in cell 0 with all of the particles in cell 1. Okay, so that means that here we'll say index I is going to be cell list of index I. And this get the next particle in cell 0. Now we've got a little bit of a problem, right? Because if cell 0 is equal to cell 1, then this isn't going to work, right? Because we're going to get stuck and we're not going to be processing the interactions correctly. So just like we did above, if we're processing cell 0 with itself, then index j is actually going to be the next particle in the list of index I. Okay, and then once that returns 0, so once index I is equal to 0 though, we've reached the bottom of cell 0, it's going to kick us out of this while loop, and we're going to go back up and we're going to look at the next neighboring cell. And then here we're going to look at next cell 0 in X, look at next row in Y, let's say, look at next row in Z. That makes sense? And so by the time we've done that, we're done. We have calculated all of the forces in our system. So this is a much more efficient way to calculate the pairwise forces than to go through every single particle. So every particle I with every particle j. That our code would just be ridiculously slow. And again, I encourage you to try it, but I wouldn't. Okay, I wouldn't ever run real simulations that way. I would be wasting my time and my career. Okay, so I think that gives us the interactions. Just right now, let's take a little break and let's see if this compiles to see that we didn't make any mistakes, and we didn't, so that's great. So now we've got our forces implemented. So the final thing we need to do is we really need to calculate, or we need to implement the velocity-Verlet algorithm so that we can update the positions and velocities of our particles. And with DPD, this is something where we need to have a little bit of, we need to slow down a little bit and think about our algorithm so that we minimize any kind of numerical errors. So let's take a look at Groot and Warren first. So here's Groot and Warren, and again, I love this paper. This is a fantastic paper for getting started with DPD. And if we scroll down a little bit and look at the simulation method, you can see, hopefully, a lot of similarities between the code we've written and what's in the paper, right? We've summed up the forces. We looked at particles that were all the different types of particles within a cutoff radius RC. Here's our conservative force, dissipative and random force. We've got the statistics on these particles, or sorry, these forces. Here's our weighting functions. It's equal to WR squared. It's a common choice, et cetera, et cetera. So what you could do is if you wanted to update the positions of your particles, then you could just say the position of your particle at the next time step, which would be at a time t plus delta t, would be its current position plus its velocity times delta t. And you would update its velocity at the next time step at time t equals t plus delta t as its current velocity plus delta t times the force that it's experiencing. So this is if you were to directly integrate Newton's second law. And then the new force would just be, you would calculate the force based on the new positions and velocities. But you get into a little bit of trouble with the random force, right? Because you've got t to the minus 1/2 here. So you've got this kind of half time step, and some of the forces depend on the velocity. So I'll let you read this paper. They talk a little bit about what's going on and how to handle this. But the bottom line is that the velocity-Verlet algorithm is one way to minimize errors. And so what you would do is you would calculate the new position of your particles as its current position plus delta t times its current velocity plus 1/2 delta t squared times the force. So this is the normal integration of Newton's second law. Where things get a little bit different is you would predict the velocity at time step t equals t plus delta t as its current velocity plus this parameter lambda times delta t times the force. You would calculate the new force using that predicted velocity, because remember, the dissipative force has that velocity term in there. And then at that time step, you'll go back and correct the force as the average of the forces that you've calculated. Okay, so this is a predictor-corrector type algorithm. And this is what we're going to do. There's a paper by Jim Polson. I forget the year on it. He's at the University of Prince Edward Island, where he goes through and looks at different types of algorithms in DPD and the associated numerical error with that. It's really good, and it's a trade-off between the number of operations required, which affects performance, and then the numerical error and things like that. Velocity-Verlet algorithm is really great. So this is what we're going to use. And if you really want to dive into this a bit more, there are other algorithms that you can use to do this. But this is what we're going to do. So we're going to get the new positions, get the new velocities, predict the new velocity, calculate the new forces, and then correct the velocities as the average. So what this means is we're going to have to store our forces and store our previous velocities. Okay, and that's why we have the fxp and vxp, etc. arrays in our code. So let's take a look at this. Let's declare the prototype for our velocity-Verlet algorithm, and then let's implement this. And it's actually pretty simple to implement, and we'll just need this parameter lambda. You can see here lambda is usually set to 1/2. It doesn't have to be, but it's a common choice. All right, let's get back to the code. So let's put in the prototype first. So we'll call this, it's not going to return anything, but we'll call it velocity-Verlet. And we're going to have to pass some parameters to it. You're going to see that we're going to have to pass prod to it so that we can pass that value to calculate forces. And I'm also going to put lambda in here just to make it a little bit more flexible, okay, in terms of wanting to change that value lambda that shows up in the velocity-Verlet algorithm. And so if we do that, let's go all the way to the end. And let's see if we want to keep this in alphabetical order. Let's put the function here. So void velocity-Verlet, and we include the production variable and the value lambda. Void, we return nothing. And let's see, we've got just a couple variables we need an index to iterate over so that we can go through all of our particles and update their positions and velocities. And we need dt squared, which is just this. I guess I don't necessarily need the 2.0, and that's it. So first thing that we have to do, we need to store the values of force velocity from the current time step. And so to do this, we'll just use memory copy. Destination is going to be the fx array from the previous time step or the current time step, depending on how you want to think about it. The p here means the value that we're storing previously, okay, the previous value. And we will copy what's currently in fx to that. And the number of values, we've got n DPD particles, and they are double precision. And so let's just do the y and the z arrays. And we also need to do this with the velocities. So we need to copy to vxp, the current value of the velocity in the x direction, like that. All right, so again, this is why I love C instead of Fortran, is C has some really nice functions like this that make my life easier. Okay, so now we need to do the first part of the velocity-Verlet algorithm, which is the first two lines of the algorithm in Groot and Warren. Okay, so let's loop over all of the particles in our system. And what do we need to do? Update the positions with the periodic boundary condition. And again, remember that make list is going to take care of applying the periodic boundary condition, but we just need to update these arrays. So x of I will be x of I plus dt times vxi plus 1/2 times dt squared times fx of I. And this will be the same for y and for z. And y and z. And actually, now that we do that, we can update the positions without periodic boundary conditions. So what you can see is that these coordinates will always be wrapped back so the particle stays within the box with dimensions Lx, Ly, Lz. these coordinates, the particle will move the same amount, but it'll just keep on going as if it wasn't bounded in the system. So we'd have a term that looks exactly the same, right? Plus dt times vxi plus 1/2 times dt squared times fxi. And that would be the same for y and z. Y and z. Y and z. Okay, so now we've got our coordinates updated. And now what we need to do is predict the values of the velocity. So what I mean is, if you look in the paper, if you look in Groot and Warren, vxi will be equal to vxi plus dt times lambda times fxi. Y and z. Y and z. Okay, so we've got our new positions and our predicted values of the velocity. So once we do that, we need to calculate the forces again. And so what we do here, what do? We make a list. This places the particles in their new cells because they've moved, right? We've updated their coordinates right here. So the particles have moved. And they may have escaped the system. And so this function will also apply the periodic boundary conditions to the x, y, and z arrays. And then once we do that, we need to calculate the forces again. And here's why we have production as a variable passed to this function. Okay, so we've calculated the forces. And now that we've done that, we need to correct the velocities. And if you remember, what that amounts to is we take the current velocity and add the average of the forces from this time step and the forces that were just calculated here. And so again, we're going to iterate through all of our particles. And we correct the velocities. So vxi is going to be equal to, not vxi, but the value that we stored previously. So that's why we stored it, vxp plus 1/2 times dt times, and the 1/2 is because we're calculating the average of these, times fxi plus fxp of I. So we're getting the average of those forces, y and z, y and z, y, z, y, z. Okay, so we've done that. And you know what? The last thing is calculate the kinetic energy. This is a natural place to do it because right here, the kinetic and potential energies were initialized to 0. So when we exit this function, we've got the value of the potential energy. Now that we're down here and we're looking at the velocities, this is a great time to calculate the velocity. So it makes a lot of sense to me to do it here. So the kinetic energy will be the kinetic energy plus 1/2 mv squared. Remember, m is equal to 1, so this will be plus, let's see, vxi squared plus vy I squared plus vzi squared. And now we've got the kinetic energy. We can calculate the temperature from that. And the equipartition theorem. So that's why we would do it. And then here we exit. So we go back to the main function. So how do we implement this? Let's go back up here to the main function. Here we calculated the initial forces. Okay, so as soon as we generate the initial configuration, we place the particles into the cells, we apply the periodic boundary condition, and we calculate the forces. So if you look down here at the velocity-Verlet algorithm, as soon as we do that, we're storing those values. So we're storing the values of the forces and the velocities. We're updating the positions and the velocities, or predicting the velocities. We calculate the forces again, and we correct the velocities. Okay? So what that means is up here in main, this is giving us the initial values of the forces for the velocity-Verlet algorithm. So now we can do the equilibration of the system. So we'll say, let's take a look at the variables. We've got t is going to be our current time step, and time equil is going to be the number of equilibration time steps. So that means that here we will do for t equals 1. T is less than time, let's make it 0, whatever. t is less than time equal t plus plus. What do we do? Well, all we have to do here is call the velocity-Verlet algorithm. So velocity-Verlet, we're in equilibration, so prod should be 0. And lambda will be 1/2. And there we go. And then now we want to enter the production stage of the simulation. So here we'll do from t equals time equal. T is less than time equal plus time production, t plus plus. Velocity-Verlet 1 because we're in production, and lambda is still 1/2. So essentially, that goes here, and that goes here. And we could calculate some stuff. And, well, what can we calculate? We could calculate RG and do that. We could calculate the temperature. We could calculate the momentum. So let's go up here. We've already written the function to calculate RG. So we could also include here double calculate temperature. And we could also include something to calculate the momentum. Let's say the magnitude of the momentum. Okay. So let's implement those, and then we should be able to put some things in here into the loops so that we get some nice output, and then we should be able to at least just run the simulation for a couple time steps and make sure that things are kind of sort of behaving. We want to make sure that the temperature converges to 1, and we want to make sure that the momentum is conserved. The momentum should be 0. And we'll just calculate the value of RG and let it go. And we should probably output the coordinate to the file every couple of time steps. And we've already specified the frequency with which we'll do that. And then we'll be done. And then what I'll do is offline, I'm going to run some simulations. And we're going to look at what the code predicts. And then in the next video, we're going to compare those results to kind of classical polymer physics theories and see whether or not this code seems to be working. Okay, so let's do this. Let's look at... Well, we don't want to put it here. We want to keep it in alphabetical order. So let's go down. We'd like to calculate the momentum. So integer. Momentum will be a double, and we will return that value. Okay, so what do we want to do? Well, we just want to loop through all of our particles. So here we'll go from I equals 0 through all of the DPD particles. And let's say we calculate p squared first because that's easy. So p is going to be, let's see, vxi squared plus vyi squared plus vzi squared. Okay, notice I've left the mass out because again, mass is equal to 1. Okay, so that's the that's p dot p. Then once we're done, what should we do? Well, let's take the square root of that and then return it. And so that should give us 0, I hope. We'll see whether or not that's true. And then let's calculate the temperature. Actually, we're calculating kBT. So remember, we set that equal to 1. So when we're done, what we expect is that will give us 1 when the system has equilibrated. So there's a couple ways we can do this. One is we could actually calculate it explicitly. So let's get, we need to iterate over all of our particles, and we need to get the degrees of freedom in our system. So what are the degrees of freedom? Well, the degrees of freedom, we've got 3 for every DPD particle that we've got. Say n DPD. Minus 1, right? Because if we have n DPD particles, really only n DPD minus 1 of those are going to be independent. So here's our degrees of freedom. And so what can we do? Well, one thing that we could do is something like this. We could say for I equals 0, I is less than n DPD, I plus plus. We would say that, let's call this KBT. We would say that KBT would be plus equals VXI squared plus VYI squared plus VZI squared. Okay, equipartition theorem. Okay, so 3/2 KBT times the number of particles minus 1 would be equal to 1/2 mv squared. And so KBT, or the 1/2s go away, right? So we've got this. And then once that's done, KBT, we have to divide by the degrees of freedom. So that's the explicit calculation, and that would work. But that's kind of wasteful for us. And remember, we're trying to make efficient code. So let's comment that out. So it's in there because it's important, but we've already calculated the kinetic energy. So KBT is actually going to be 2 times the kinetic energy divided by the degrees of freedom. And then we could return. Because at each time step, we are calculating the kinetic energy K, and that variable is shared. So there's no sense in doing this loop through what could be millions of particles when we already have that value calculated. So why do it? So let's say use the kinetic energy calculated in velocity. And that's a smarter way to do it, in my opinion. So let's save this. Let's go back up here and let's see what we want to output to the user. So we've got a value for RG RMS, double, let's call this temperature calculated, calc, and yeah, we'll just keep it as RMS. Okay, so now we're going through and we're running the velocity-Verlet algorithm. So we could say, let me remember the names of these things we defined: calculation frequency and output frequency. So down here, we would see, let's do modulo division, right? So if T modulo division calc frequency is 0, that means that T is a multiple of calculation frequency. Then we can say RG RMS equals calc RG. The temperature calculated would be calc T. And the momentum that we calculate would be calc P. Did I get the case right on those? I did. Okay, so we've got those values. And let's say that we do this. So let's print to the screen. Let's make it look kind of nice. We would have KBT. Let's say this is 2 points. Let's get 5 decimal places. Sounds good. The momentum. Let's do the same, 2.5. Float. RG to the 1/2. So the root mean squared, well, root mean squared radius of gyration. Let's say, let's do the same. So we'll output those values to the screen so the user knows what to do, and it'll be the time step, the calculated value of the temperature, calculated value of the momentum. And to be honest, I usually like to keep track of these in a file just so I can go back afterwards and make sure everything's okay. So let's put a file in here. Let's call it data output. And so we might as well output those to disk. And so let's say that data output equals, let's open temperature.dat. Let's append to it. And let's print to that file the time step and the temperature. So this will be T and T calc. Okay, so output temperature to disk. Okay, and now let's just do this. The momentum, just in case something goes wrong, right? We'd like to be able to track the momentum and make sure that it's not diverging, because that would be a sign that something is wrong in our simulation. Okay, and time step and the momentum. And then output RG to disk. And this is really the important one, right? This is the kind of thing that we would use in our research in a publication. So let's do this. Radius gyration. And we will append to it data output. And I'm writing out more or less the full precision here. So this is T and this is RGRMS. And we close the file. So all this stuff, we're doing it in the equilibration. We also want to do the same thing in the production steps. So this is what, 127 minus, so this is what, 21 lines. We also want to put this down here where we're doing the production step. Okay, so we're doing the same thing. And let's just make sure that we close our loops. That's good. Okay, so we will output all this stuff to screen, output it to file. That's good. We have this other one. Output frequency is 1,000, right? We don't want to write the coordinates too frequently because these files can get really large, and it also slows down our simulation. So every 1,000 or 10,000 time steps would make sense. But when that happens, we want to write our coordinates to file. So we want to call write XYZ, specify the file name and whether we want to append. Notice up here when we first write out, we said the initial config, we set append equal to 0 because we want to generate a new file. We don't want to append anything. Down here, though, we might actually want to append. So let's say over here, if T modulo out frequency equals 0, we will write XYZ trajectory, and we do append so that we can generate a movie. And I will show you those movies in the next video so we can get an idea of what our simulation actually did. And I think that should do it. So let's take one last look, and then we should be done. We calculate the initial forces, velocity-Verlet algorithm, production is equal to 0. We're equilibrating. We write to disk. We write to the screen. We write the coordinates every certain amount of time, every 1,000 time steps right now. Once we're done equilibrating, we start the production step, and we call velocity-Verlet with 1 to signify we're in production. That makes sense. And we do the same thing. We write to the same files, and then we write the trajectory, and then we end. So yeah, this should work. Let's just test this and see if it compiles. Does not compile. What did I do wrong? I am short a value. Okay, well, that's easy to fix. Let's go to line 67. We forgot what? We forgot RG. That means we also forgot it down here. Okay, and square root of p, we forgot to declare a variable in calculate momentum. So let's just say return square root of p, and now it should compile. Lovely. So that's it. Let's take a look at parameter and see how our simulation will look. So we're going to look at a 32 cubed system, fluid density of 3, that's normal. 5% polymer, degree of polymerization 10, bond length 0.7, sure. Temperature is equal to 1, or kBT is equal to 1. Strength's the same, harmonic strength, sure. Integration time step, sure. 10,000 equilibration time steps and 1,000,000 production time steps. Looks good to me. Let's run it and see how our code does. So this is what our code output. And it's puzzling to me, and it's puzzling to me because I've done this many times. And I noticed a couple things. First of all, this temperature here, this value of kBT, it should be 1, and we're getting 0.98. That's much lower than I expected. That's like over 1% error. And in my experience, that doesn't happen with DPD. We said the momentum should be conserved. So the value here, it's not changing very much. But notice that it's not equal to 0. So I expect that this to be 0. The other thing is if we run this code, look how fast it's running. I would love it if my code would run this fast for a system that's 32 by 32 by 32. So something's off here. There must be a bug in the code. So let's take a look at the code and see where that might be. If we go to calculate forces, let's see what we're doing. To me, the fact that the code is running so quickly means that down here, we must be skipping this because this part of the code, this is the bulk of where our time is spent, and it should be running much, much slower than this. And my suspicion is that we're not looping through all the cells. And my suspicion is correct because look, I'm declaring nx, ny, and nz here. I shouldn't have declared these. This means that I've got these variables, and the scope of these variables is this function, which means that I'm not seeing how many cells there actually are because these values are global variables that were calculated already. So I need to get rid of this. I suspect that if I do that, the code will take more time to run. So that's the first thing. I don't think we were calculating the conservative, the dissipative, and the random forces. We'll see if that's true. The second thing is the momentum was not equal to 0. So let's take a look down here and see what we're doing. What we're doing is we're calculating the sum of the momentum squared for all of the particles. That means that this quantity here will never be negative, which means that things can't cancel out and you will never get a negative, or you'll never get 0. You can't get 0. So this is not the correct way to do this. Let's get rid of this. What we actually want to do is let's compute the components of the momentum. So let's do a vector addition instead of adding the magnitudes. So px, let's initialize them first. Pz is 0.0. Okay, so let's do that first. And then let's add vxi, vyi, vzi. So now we add the components, and now there's the potential for this vector to be 0. And so we'll get the magnitude of this vector. So let's see, px squared plus py squared plus pz squared. And we will return the square root like before. So I suspect that this will give us 0 for the net momentum. Okay, so two things. We deleted those 3 variables so that we actually loop through the cells. We weren't doing that before, is my hypothesis. We calculate the momentum correctly, and that's it. So let's exit and let's recompile the code, and let's see what the code gives us this time. Right off the bat, we notice the momentum is 0 and it stays 0. So that's fantastic. So the momentum is conserved. Notice that the temperature now is changing. It doesn't just stay at 0.98. It shoots up above 1 and then starts to decay. This is the normal behavior that I expect for the simulation. So I'm going to sit here. Let's just let this run for a few time steps and check in a second and see if the temperature comes back down to 0 and if the momentum stays as 0 and if the radius of gyration levels off. So let's just give this a bit and I'll check in with you in a couple minutes. Okay, so two things I hope that you can notice from this. One is that KBT has decayed very close to 1, so that's the behavior that we expect. It took a little bit more time, that's why I sped up the clips. And the momentum has remained 0, and the root mean square radius of gyration has increased, and it seems to be stabilizing roughly around 1.12 to 1.15 RC. So maybe one last thing that we'll do is we'll take a look at some of the data that's been written to disk. We'll take a look at the configurations in Ovito, and we'll compare this to a previous simulation using a different code to see how these results agree with or don't agree with what's been published in the literature, and then we'll wrap up for today. If we take a look at what the code has generated, we've got everything that we would expect. We've got a file with temperature. We have a file with the momentum. We have a file with the radius of gyration, and actually, I modified the code slightly and didn't tell you to output the average bond length, okay? So we've got about 0.77, 0.78. We'll see how stable that is, but I want you to compare that value to what's in the configuration file where we set it to be 0.7. Okay, so we set it to be 0.7, but due to other forces in the system and the strength of the harmonic interaction and things like that, it's not going to be exactly that. So I thought we would plot some of these values to see whether or not they make sense. And so the first thing that I usually check is I want to check the behavior of the temperature. And you can see here, this is typical behavior for a DPD simulation. We started off at an initial temperature of 1, so KBT was equal to 1. But the particles were at random positions. They weren't subject to any of the forces and things. So initially, the temperature increased quite a bit as things started to rearrange themselves. And then the temperature decayed such that it was very close to a value of 1, right? So we're like 1.003 or something here. So that's good news. It means that the temperature is behaving. This is a sign that our simulation code is correct and that we're processing all of the interactions correctly. Another thing we can check is the momentum and see that it remained 0, and you can see it flatline. So momentum is exactly 0. That's great news. Next thing we can do is we can plot the radius of gyration to see whether or not it's converged to a kind of an equilibrium value. And so what you can see is that the radius of gyration initially increased, and it kind of increases a little bit. You'll see that this fluctuates a bit, and it still looks like it's increasing a bit. So we're certainly not at equilibrium, but we can kind of get a rough estimate of what the value would be, and we're looking at a value of 1.15 right here. So that looks good. We can take a look at the bond length. That's the second, or actually it's the third column of this file. And so the bond length fluctuated quite a bit initially, and you can see that it shot up to be something pretty big, and then it decayed down as the harmonic force was taking over and setting some value. So this is good. It looks like the harmonic potential is behaving. We've got the coordinates to look at still, and we'll come to that in a second, but I wanted you to look at the value of the radius of gyration here. So if we look at this file, again, we're looking at 1.13, 1.14. This is still increasing, but this gives us at least an approximate value to kind of compare to. And so let's take a look at a previous publication of mine using a different code, using the parallel Fortran code that my group uses, but with similar parameters. And let's see whether this radius of gyration for a chain length of 10 of 1.14, 1.15 makes any sense. So here's a paper from 2021. It was actually accepted in 2021, published in 2022. And we used DPD with some modifications to look at the behavior of polymer grafted nanoparticles. But as part of this study, one of the things that we did is we looked at just free polymer chains. And so we do have some data on how these things should behave on their own. So if we scroll down in this, in the supporting information, there's actually a table that has the values of the radius of gyration for these polymer chains somewhere. Here we go. And again, the bond length in this paper was set to 0.7, but instead of using a harmonic potential, this paper used a Feeney potential, which is a little bit stronger than the harmonic potential. But you can see that for a degree of polymerization of 10, the equilibrium value of the root mean squared radius of gyration was 1.15. So that agrees really well with what this brand new simulation found. So that's, again, yet another sign that the code is generating correct results, because a completely new independent code using similar parameters gave us similar values of this physical quantity. And our code should agree at the end of the day unless there's something wrong. So that's a good sign. And then the last thing that we'll do for this video is let's just take a look at the coordinates and the evolution of the coordinates across the simulation to make sure nothing funky is happening. Make sure we're not losing particles to the environment, that our system's not blowing up, anything like that. And then we'll have some confidence that this simulation code is correct. And then in the next video, we'll go over some results that were generated with it that you can compare with your own code. So in Ovito, I've loaded in trajectory.xyz. Now remember, in the code, we set output frequency to be every 1,000 time steps, and we went to about 7,000 time steps here. So there's 7 snapshots. Again, we're only rendering the polymer chains, and so you can see a couple things. First of all, you can see here's a polymer chain, here's a polymer chain. Here's 2 monomers, right? And this is the result of the periodic boundary condition. The 2 monomers here belong to a polymer chain that's on this side of the system. The 1 monomer here that seems off by itself belongs to the polymer chain down at the bottom. So that's what the periodic boundary condition is doing, and it's looking like the periodic boundary condition is working just fine. The only other thing that we'll do in this video is I'm just going to press play down here, and we're going to just loop across all the different snapshots that were taken, the 7 snapshots that were taken as the code was running, and make sure nothing weird is happening, make sure particles aren't flying out of the system or anything like that. That can happen if you set your time step to be too large, so if dt is too large. That can also happen if there's some bug in your code. So let's take a look. You can see the particles are moving around, but nothing's escaping the system. So that's a good sign that everything's working as it should be. So again, that's it for today. In the next video, I'm going to come back. I'm going to run some simulations on chain lengths of 10, 20, 30, 50, and 100. And I'm going to do that in solution and in the melt state. So I'll set the volume fraction of polymer to be 1 instead of 0.05. And we'll look at how the radius of gyration scales with the chain length and see if that agrees with the Gaussian chain prediction and the self-avoiding walk prediction. So the good solvent prediction of Flory. And that'll be it. And then you're free to, I'll come up with some suggestions for things that you might do with your code in the future. But at that point, you'll have a pretty good understanding of how to write this code, and you can expand on it to make it parallel, look at different polymer architectures, you name it. So until next time, I'll see you then.